Hey, so the first thing I wanted to do is just address the title of the video. You guys may have heard of these AI software engineers that are coming out like Devin. I personally don't think these are ever going to replace software engineers. I've been a developer before, and the work that developers do just cannot be replaced by AI. I think AI might change the work that developers do, maybe make them a little more efficient in some ways, but software engineers are not going anywhere. That being said, whether you are a developer or a data scientist or a machine learning engineer, there are 4 ML concepts that I think everybody should be familiar with, and that's what we're going to go over in this video. And I'm not going to waste your time and leave like the most important concept for last or anything like that. Let me just tell you what 4 concepts we're going to talk about. The first is training. So it can be really annoying when people talk about models training or learning a relationship without being clear as to what this actually means. So let's talk about what training is first at a high level. Then we'll talk about linear regression. You may have heard about it in like a statistics class before, and it's actually like the foundation of AI and neural networks. So it's definitely a critical topic to be familiar with. And then we'll talk about what a neural network actually is. It's actually just an extension of linear regression. So if you understand linear regression, neural networks are not that bad. And the last topic we'll talk about is gradient descent. This is kind of taking away the black box around training and going even lower level, right? What is the actual algorithm? Like what is the actual sequence of steps? What's going on in the code? It's just a simple for loop actually to actually train models. So this is the order of the topics, and let's get into it. Okay, so let's talk about training. It turns out it just means that we're minimizing a function. If you've taken a calculus class before, you've probably had to minimize some kind of function. We can talk about a super simple function like y equals x squared, like a basic parabola. We have y equals x squared, excuse my mediocre handwriting, and we can see that the minimum of the function is right there. So we could use calculus to do this, or we can just see it. So what function are we actually minimizing when we are training ML models? Because we're not minimizing this simple function. We're actually minimizing a way more complicated function. So it turns out what we're actually doing is just minimizing the model's error, specifically the error on the training data. Let's say we're building a model to predict how tall someone's going to end up being. And our 3 inputs are like how tall they currently are, what their current weight is, and the average of their parents' height. And our data set might have this information for like a few thousand people, and we have their ultimate final height that they ended up becoming. So the model's error is essentially just the difference between the model's prediction for how tall someone will end up being, someone actually in our training data set, and the actual true height that they ended up becoming, the answer that's in the data set. So what does the error function look like? It can really vary depending on the ML model. It might just be something like this. It could be totally different. But ultimately, if the y-axis is error, if the y-axis is the model's error, essentially the difference between the model's prediction and the true answer, all we're trying to really do is minimize this error. Because if the model's error on the training data is minimized, then it's actually doing a pretty good job of predicting the right answer for those training data points. And that means we think it might generalize well to people it's never seen before. And the x-axis, we're just going to keep this a little high level for now until we get into linear regression and neural networks. But the x-axis, these are the model's parameters. This is what the model actually uses to make its prediction. You may have heard the term weights before, model weights. This is what the model actually uses in its mathematical formula to make a prediction. So when we talk about minimizing the function, we just want to know what is x? What is x equal to over here? So if we know the model parameters to actually minimize the error, then we want to use those model parameters to actually make later predictions. And don't worry if that didn't make perfect sense. It'll make more sense as we talk about linear regression. It'll make complete sense once we get to the last topic on gradient descent. So linear regression, this is actually the simplest AI model possible. Let's use our example earlier of predicting how tall someone will end up being. All it is saying y equals w1 times x1 plus w2 times x2 plus w3 times x3 plus some constant term b for bias. It's kind of like the b in the famous equation y equals mx plus b. So y is actually the model's output, it's its prediction for a given data point, and x1, x2, and x3 are the inputs to this model. So those are those 3 characteristics for a given person: their current weight, their current height, and the average of their parents' height, respectively. The actual order of them doesn't really matter. It could be x1, x2, x3 in that order, or it doesn't really matter which variable or which input we talked about, like height or weight is x1 or x2, etc. And the model parameters that are actually going to be learned and updated during training are W1, W2, W3, and B. These are the model parameters. But what do these parameters actually mean? We can see that W1 multiplies X1, W2 multiplies X2, and so on. So these parameters, when we call them weights, right, W for weights, this is actually just representing the significance of that input in actually predicting our final answer. So if we have a really high W1, this really means, like, if after the model is done training and learning, we end up with a high W1, it means that X1 is really important in predicting Y, right? So if we end up with a really high W1 and X1 is the average of your parents' height, if that's what that input variable represents, then it just means that that's something that's really important in predicting how tall you'll end up being. So these W's, these are just like weights, or actually they're significance numbers, right? They are actually measuring how significant are X1, X2, and X3 respectively in predicting the final answer. And what's the point of B? So before we answer that, I just want to clarify that before we actually train the model, we have totally random values. We start off, so these are initialized. These are initially totally random. We start off with random values for the model parameters, and they're actually changed and updated over that giant for loop called training. It's actually the algorithm called gradient descent. That's what we're going to talk about last. So these start off totally random, and they actually adjust and eventually get to what they should be so that the model's output Y is pretty good and pretty close to what the actual output should be for every person in the data set. So what's the point of B? Well, you can think of B as kind of like a base height, right? No one's ever going to have a height of 0, right? So we all might want to add some number to everybody's height, kind of like a base height. And this is also learned. It's just a parameter, just like the weights. Okay, if you're still watching this video, that's awesome, because all the NPCs already clicked off this video. Neural networks are just an extension of linear regression. This input layer of nodes over here is just where we pass in the X1, X2, and X3 that we talked about earlier. So we have X1, maybe that's the average of your parent's height. We have X2, maybe that's your current weight. And we have X3, maybe that's your current height. And then all these nodes, right? This node over here, this node over here, and the two below it, they are also just doing linear regression. You can see that each of these nodes, this node, and the two below it, each of those nodes is fully connected to all of the 3 input nodes in the layer before it, meaning each of these nodes, this node over here, and all the 3 below it, they're all using that equation to actually get the output number, or activation as it's called, for the respective node. So we can think of the number being stored in each of these input nodes as being an input variable, X1, X2, or X3, depending on which node we're talking about. And all of these nodes over here, all 4 of these hidden nodes, are actually storing the outputs, the Y values, based on the X1, X2, and X3 in the previous layer. But here's the catch. Each of these 4 nodes, right? We've got one here, and the 2 below it. Each of them is learning its own set of W1, W2, W3, and B. So each of these nodes has 4 parameters, right? This node is learning 4 parameters, this node is learning 4 parameters, and the same case for the 2 below it. So all of those nodes are actually doing linear regression. So what about these output nodes? What's going on over here? We've got 2 output nodes. Each of those nodes in the output layer is fully connected to the 4 nodes in the previous layer. So each of those is using this equation. So we can actually think of these 4 hidden values, the Y1, the Y2, the Y3, and the Y4. These are basically the inputs, or the X's, for the next layer. So since we had 4 numbers in the hidden layer, it actually goes and adds a W4 and an X4, right? A 4th term, actually a 5th term to this equation, right? Because we have 4 weights and 1 bias for a total of 5 parameters. We have 5 parameters in this node and 5 parameters in this node. So when all said and done, this particular neural network is actually outputting 2 numbers, right? We have the output of this node over here and the output of the node below it. So then what we might do is we might just take the average. We could take the average of Z1 and Z2, and we could actually return that as the output, or the model prediction. Okay, our last concept. Gradient descent is the algorithm that actually updates W1, W2, W3, and so on, all the different weights in our neural network, and the biases B over training. Okay, so here's the pseudocode. We're going to step through it and explain what each line is doing. Remember, our goal is to minimize the error, right? That's what gradient descent does. So we'll decide beforehand a number of iterations to run this algorithm. And the more iterations that we run the algorithm, the better approximation we'll get for minimizing the error. That is how training works. This is the training loop, as it's called. So the first thing we need to do is we need to get the model prediction. And this is just going to use the current weights, right? The current values for the parameters, so the W's and the B's. So what we pass in is we pass in X, and X is our training data set. Let's say X is an n by 3 array. So n for the number of people in our data set, and 3 is actually the number of attributes that each person has, their current weight, their current height, and the average of their parents' heights. And then y will be an n by 1 array. For every person, we have whatever the model's prediction is for how tall they'll end up being. Then we need to get the current error. So you can think of truth. Truth over here is another n by 1 array. For every person in our training data set, we have a number that represents how tall they actually ended up becoming. And the next line might seem a little weird. If you remember derivatives from calculus, it's just the rate of change of a function with respect to some variable, right? So what we're going to do is we're going to calculate the derivatives. And this is as crazy as the math is going to get. Let's say we have our error function and we call it e. We want the derivative of the error function with respect to every single weight. So we want the derivative of the error with respect to W1. We want the derivative of the error with respect to W2. So that's dE over dW2. And we want all of these for all the biases and weights in our network. So that's what the get derivatives function is going to do based on the error, right? To calculate the derivative of this function with respect to the weights, it turns out it depends on the value of the function. It depends on the error. So that's why we pass that in, and this function is going to do some calculus and give the derivatives back to us. Using those derivatives, which we're about to explain what this update parameters function does next, but using those derivatives, it will actually update all our W1s, our W2s, all our biases, and let's just say that those are stored as some sort of instance variable in whatever class we're dealing with here. So that's why I haven't actually declared those as variables. They're just actually the state of this class in the background. Let's not really worry about that in the pseudocode. But after we calculate the derivatives, we're going to call the update parameter subroutine, which is going to update the state of all of those parameters. And then we simply go back to the top of the loop and do another iteration. And hopefully this time, with our updated parameters, the model's prediction is a bit better, meaning the error will be a bit less. If we repeat this for enough iterations, the model will quote unquote learn the relationship between the data points in the data set, and the error will actually be as low as possible. And that's gradient descent, but there's still a couple things that we left as a black box. Get derivatives. What's actually going on in that function? So machine learning engineers rarely ever do these derivatives by hand. We have libraries that can calculate those for us, but ultimately what we do need is the derivative of the error with respect to W1, with respect to W2, and so on. But what about the update parameters function? How are we using the derivatives to update the weights? This is actually the main formula behind gradient descent. And here's the formula. The new W, so for W1, W2, this could even be for a bias, the new value of that parameter is simply equal to the old value of that parameter minus the derivative. So minus the derivative, specifically the derivative of the error with respect to whatever weight or parameter we're talking about. And this was calculated in the previous line of code, times some value alpha, which is called the learning rate, and it's typically a number like 0.01 or 0.001. So to actually understand exactly why we're subtracting out the derivative times alpha and why after doing this for a lot of iterations, we end up with a pretty good approximation for what the weights should be, such that the model gives a pretty good answer, that's actually a separate video. I've got a 5-minute video, just a 5-minute video that builds the intuition for why this equation works, and it should pop up soon. So I hope you found this video helpful. If you're still watching, be sure to leave a like on the video. Apparently it really helps the algorithm and help this video get promoted to other people, and hopefully I'll see you soon.